Well, welcome back. This is following on from the video where I demonstrate a portable software-defined receiver that you can buy online from, say, Banggood or some of these online places in China. And I just wanted to explain a little bit about the mathematics of how you demodulate signals on them. There's a couple of architectures, well, a number of sort of architectures that are used, however, so it's not quite as straightforward as you might imagine. This is probably the easiest one to understand, but it's probably not the most up-to-date method, where you've got an analog front end on your receiver and a mixer that's a local oscillator, which gets you down to IF, the intermediate frequency. Now typically that's about 10.7 megahertz. That's like in a normal radio receiver. All the analog receivers have used that since the days of the invention of Armstrong's invention of FM. I think that was his idea to do that. Armstrong was the inventor of frequency modulation. In AM, that would be 455 kilohertz traditionally. So anyway, you can sample that, and then digitally you can multiply the signal by cos and sine. That's what DDS, direct digital synthesis. And then low pass filter, and then downsample K to 1, and that gives you I and Q, the so-called quadrature and in-phase components. Let's say this one would be the in phase, this one would be quadrature because it's 90 degrees shifted. So you're multiplying by cos and sine effectively here. And then in here you need some formula to demodulate, and then you shove it out the digital to analog converter. So that would be one way to do it, and I'll talk about another way in a second, but let's look at this first. Here you've got to sample quite a high frequency really, but that actually was a problem before the year 2000 or so. I think the A to D converters had too much jitter on them and weren't really satisfactory for that, but they began to become more useful after about the year 2000, and we're at this stage now where we can we don't have to sample at huge frequencies. If you've got a band limited signal, remember Shannon's sampling law says that you only need to sample at about twice the bandwidth of the signal, greater than twice the bandwidth, not twice the highest frequency, where a lot of people get that kind of mixed up. It's twice the bandwidth, greater than twice the bandwidth. So if you've got an AM signal, for example, it might only be 5 kilohertz bandwidth. So you need to sample just greater than 10 kilohertz or something. But as I say, you wouldn't have been able to do that in traditional A to D analog to digital converter in the past, but it's possible to do that now. So that's one way it can be done. So you need these cos and sine terms here, and I'll just show you the maths behind that, where that comes from. It's easier to show you in analog rather than in digital. The digital is just sampled versions of the analog, so it's, the maths is exactly the same really. But if you've got a signal at the IF filter in this form, which is Y is R of T cos and omega carrier T. Omega carrier is the carrier frequency. Now this is an FM term I've stuck in, which means it applies to FM, but I've also stuck an AM term in, so it can do AM or FM. I just put it in as a general thing. And the phi that was in from a previous video when I was looking at multipath interference and how to get rid of it using the amplitude lock loop methods. So you could consider that to be 0 if you wanted to, but it doesn't make any difference to the maths in the end. That just sort of follows through. So in reality, unless you've got some fancy problem like multipath interference, you're not going to have amplitude and frequency modulation at the same time necessarily, unless it's noise. So it would normally be RFT cos omega carrier T for AM, or RFT and then this bit here for FM, where R is 1. It's usually kind of limited, what used to be traditionally limited anyway, so that to get rid of the amplitude modulation. And this is the sampled version, but let's jump a little bit and look at these two triggered entities, which you learn when you're at school. cos A cos B is half cos the sum plus a half cos the difference. Sine A cos B is a half sine the sum plus a half sine the difference. I think I got that right. Now go back to our original intermediate frequency filter output. So this would be sampled, but I'm just assuming, you know, this is a sort of analog version of it. So you could do this in analog if you wanted to. If you multiply this guy here by cos omega carrier t, of course it's not going to be bang in phase with that, so I mean I suppose it should be cos omega carrier t plus an offset, but again that's not going to make any difference here. You're also going to multiply it by sine, but the cos and the sine have to be 90 degrees apart. They've got to be rock solid, so that's best done in digitally, so you can get a cos and a sine term. Multiply it by cos and you get cos of omega carrier t times r of t times cos of all that, and using the cos trig identity you get half cos the sum plus a half cos the difference. So the 2, for example, doesn't make any difference. We can rescale this by a factor of 2, so you know that's not relevant really. You'll notice the phase term is apart from the carriers disappeared, because we've got the cos of the difference here of omega carrier times omega carrier plus this lot. So the carrier term disappears and you're just left with this guy here, this bit. And then you get another term which is at twice the carrier frequency plus the phase term. But fortunately for us, that's at a very high frequency. Let's see, if the IF was 10.7 megahertz, it would be at 21.4 megahertz. So we can put a low pass filter in and delete that and, well, reduce its level so that it's not significant in any case. So this leaves us with a baseband signal RT over 2 cos this, depending on whether we've got AM or FM or whatever. Then we can do the same with sine, and half sine the sum and the difference plus the difference term disappears and you're left with that. So these are the terms we call the I and the Q, which would be digitized, as I say. It wouldn't be I of t, it would be I of k times t, the sampling interval, but it amounts to the same thing, and you've got that. So depending on whether you've got amplitude modulation where you wouldn't have this bit in here, or whether it's just frequency modulation and you'd have this bit in here, maybe no R of t at all. So to demodulate these signals for amplitude modulation, it's just the square root of I squared plus Q squared, because what happens is you get R squared cos squared of this plus R squared sine squared, and cos squared plus sine squared is equal to 1. So you're left with R squared. If you take the square root of R squared, you get R. So that's the envelope of an AM signal. And then to get the phase, it's the arctan of the imaginary over the real Q over I. But I should point out, and I did in a previous video, that that's not how you demodulate FM, I beg your pardon, because FM is the rate of change of phase. That would be for phase modulation. And you still have to do this horrible arctan thing as well. So there is a way around that, which I mentioned in a previous video. I might sort of go into that in more detail in a minute. But I'll just show you this working on AM, since and then I'll show you working on FM and sort of get back to the maths again. So I've simulated this, spent an hour or two with, if I can find the damn thing. Where's it gone? Oh yeah, it's in here. Should be here under AM. Ah, there it is, AM with IQ. I'll run this in a second, but so this is our amplitude modulated signal, and this is our software radio, if you like, a sort of simulation of the software radio demodulated form. So what we've got here is in the program, here I'm generating AM. That's just the cos of the, well, here's the carrier term, and it's getting multiplied. Oh, that's the baseband term, sorry, Where's the, oh yeah, this is the carrier term here, cost for the carrier, and that's the baseband signal that gets multiplied by. There has to be a 1 in AM, so it's 1 plus M cos omega modulation T times cos omega carrier T. That gives you AM out there. And then to demodulate it, I've got this sub called IQ, and what that does is it multiplies our IF signal as it is there, working at the IF frequency, by a cos term and a sine term, 90 degrees, and then we low pass filter, in this case at what's that, at 100 kilohertz I think it is. Yeah, I mean that you can fiddle around with the orders of the filters and so on. That wouldn't be done with an IIR filter, that would be done with a FIR filter, and probably a very sharp one, and a digital DSP processor. Let's just see it working. You get a lovely clean result. So let's just vary the frequency. Oops, there it is. I've just made it bandwidth up to 5 kilohertz because that's typically what a AM signal is, and here's a demodulated signal. Of course we can get that in an analog receiver just by rectifying and then low pass filtering with whatever method, you know, much simpler in a way. But if I vary the modulation index, goes up to 1 here quite easily, hardly any distortion, down to 0 where you get DC out, which is quite interesting. When it says no modulation, you get a half coming out. And then we have, so that's using the IQ method to demodulate AM. Now we can do the same with FM, but it's a little bit more complicated because you've got the arctan function in there, and I'll just explain that. So this is if this is the sampled version, I've just written it as P of n. So n is 0, 1, 2, 3, 4, and so on. What you want to do, have to do is differentiate with respect to n. It's like time, the arctan function. And if you differentiate arctan x, it's easy. It's 1 over 1 plus x squared, I think, if I got it right. But then you have to differentiate the term within it. It's a function of a function. So you end up with this thing, I times the derivative of q minus derivative of I times q over I squared plus q squared. You recognize that I squared plus q squared, that's the envelope squared. If you take the square root of that, you get, that's the envelope itself. So that's the envelope squared. It's interesting you get that. So we have to be able to differentiate q and I then. And the simplest way to do it is with a first difference, a so-called Euler differentiation approximation. It's not the best way to do it. It's a very crude way to do it, in fact. So in other words, I just assume that the differential of I of n is in minus 1, and the differential of q of n is qn minus the past value qn minus 1. So all I need to do is store the previous value and then take the difference. That's what we do in a PID controller. That's the differential part of a PID. Normally we consider that to be very noisy, and you know, because it goes up at 6 dB per octave or whatever. So that can be done with, you know, smarter ways with digital signal processing. But anyway, we end up with this formula here. This isn't my formula. I don't know where I got it from a long time ago. Q of n times I n minus 1 minus I of n times q n minus 1. So the current value of q, the current sampled value of q times the previous value of I minus the current value of I times the previous value of q divided by I squared plus q squared. And that's the demodulation of FM. Then we don't, the other way would be to somehow use this arctan and differentiate it with an approximate differentiator, and that's another way to do it. But I've shown you this working before in a, let's hope this works. Yeah, okay. So this is FM. It's a lot more complicated. So this has got an AGC in it. It doesn't need to have an AGC in this particular, for this demo, but I put it anyway. That's, you can't see it because it's only got a constant amplitude. It's in there somewhere, the FM. and that's me varying the frequency, and that's the demodulated output of the FM signal. And if you want to see the program software, there's my envelope I squared plus Q, my envelope squared, I squared plus Q squared is the R squared, and then I need to store the past value of Q and I, and that's done by registers. So I take my current value of I, let's say, and I put it here in the loop, and this is for loop, and then I take the previous value, so that gives me I n minus 1, and likewise for Q would be Q of n here. That shouldn't be like that. That's just, sometimes these guys, move around. Qn minus 1 is there, and Qn is there, and then we just implement that formula basically. This bit here is to do with multipath interference, which is another video, so forget that. And that's how we differentiate. That's how we demodulate FM. So it can be done right down at baseband. But apparently that's an old idea really, and the more modern approaches, if you look at this article on embedded.com, how software-defined radios handle ultra-wide frequency tuning, you can kind of sample the whole spectrum, which it seems that if you can get away with it, a better way to do it rather than the analog front-end idea, so you can get rid of the analog stuff altogether really. And this little table summarizes it. You use this method called direct sampling. Well, just read it here. Direct sampling refers to sampling signals directly from the antenna. Well, that would actually be, it wouldn't be just from the antenna, it would be from a low noise amplifier connected to the antenna, of course, with minimal or no analog components in between. So you take a huge chunk of the radio frequency and sample it, and then you pass it on to the software. So then you've got hardly any analog components. Everything's done by software. This is the one I've just talked about, which is the IQ, which is hardware followed by software. And then there's this super heterodyne version, IF down converter, a second mixer. That's to reduce what's called image frequencies. You can down convert twice. Some of the posh radio receivers in the past used to do this. Down convert once to one IF and intermediate frequency, and then down convert a second time, and you get the image, what's called the image frequency rejection, using that method. So the hardware here is a little bit beyond me because I don't work, but it mentions here that you can sample up to 3 gigasamples per second. So it allows for huge amounts of data to be digitized. Obviously you can't put that data into a micro, it's going to be too much, so it has to be decimated and downsampled once it's sort of converted to the baseband signal, because the sampling rate's too high. And there's a bit more information in there, but that's a very rough idea of what's going on. I'm sure you can look up the rest yourself. Thank you very much. See you next time.